All right, in this video we're going to be looking at two main things. So first of all, we're going to be solving like problems that are the analog of F equals ma. So sum of the torques equals I alpha. So we'll look at some common types of problems, and actually this example here is one of them. So you have two hanging masses, and we're no longer going to ignore the mass of the disk. So whereas while we've looked at a problem like this before, and we would say that the tensions in the ropes were equal, but actually without so we assumed that the disk was massless, but now we're going to give it some mass and see what why the two tensions should be different, and actually show how we set up equations that we could solve for T1 and T2. So actually here we're just asked for the acceleration of the system, but hopefully in the process of setting up the equations you'll see how you could solve for T1 and T2 as well. It gets a little bit more algebraically messy, that's why we didn't solve for them. Okay, so that'll be the first half of the film, of the video. And the second half we'll talk about conservation of angular momentum. So really it's kind of like the same equation, except if you set tau equals 0, then angular momentum is conserved. But the problems have like a different flavor. Just like, the problems that you did with F equals ma were different in flavor versus the problems you did with conservation of momentum. So we're just looking at the rotational versions of those two things. Okay, so I'm going to write down, I'm going to do this for the angular momentum part of this video as well. I'm going to write down some translational statements, and then I'm going to see what the rotational analogs are, just using our table of replacements. So as a review, what we said before was that if you had the sum of the forces, this is equal to, you could write it as dp dt. You could write the momentum as mass times velocity, take out a mass, m times a. Right, and we use sum of the forces equals mass times acceleration a bunch. The rotational version of this is sum of the torques is equal to dl dt. We could also write, for a rigid body, we could write the angular momentum is I times omega. So we're going to relax the assumption that L equals I omega in the next chapter. We'll start to look at a little bit more complicated objects. But for now, we'll just say that we have a rigid body where we can write this. And if I is constant, we could take it out of the derivative and say that this is I d omega dt, which is alpha. Okay, so if you remember what's going on in the translational and you remember your table of what the rotational analogs are, then you can get to the rotational versions of these formulas pretty quickly. So what we're doing is just applying this formula. So we'll look at this, we'll talk about angular momentum when we talk about momentum. So remember when we talked about the translational equations, we used F equals ma even before we talked about momentum at all. So we're going to do the same thing in this video. We're going to focus on sum of the torques equals I alpha. And then part 2 of the video, we'll look at the angular momentum piece of this. Okay, so this will be our star equation for part 1. Okay, so your book does an example right here. So I'll just talk about section 10.5. It's like your book does two quick examples. 10.5 and 10.6 are two examples. So it's like an easy example and a medium example, or medium and hard, depending on whether you've seen this before, I guess. So we're going to do like an example that's really similar to the example in 10.6. So before I do this example, though, let me just review the example in the book. So the example in the book is looking at merry-go-round. So this right here. And at first he says, well, so just have one thruster and you could get the merry-go-round like this. Unfortunately, though, then the rocket would be providing a net force on the merry-go-round, and the axle at the very center of the merry-go-round would have to provide an equal and opposite force. So actually, this puts a lot of stress and strain on the merry-go-round. There are other things going on. maybe we'll get to it when we talk about statics. So to take it easy on to get this thing to rotate, but taking it easy on the axle, this would be a nicer arrangement to have 2 rockets. So there's no net force on this thing, but there is a net torque. Right? So see how the 2 forces. So another reason I'm writing down both of these equations is that both of these are true and going on at the same time. It's not like you have to do one or the other. So what's going on in this example is that the sum of the forces is 0. That's true. And the merry-go-round does not accelerate. It doesn't do any linear acceleration, but it is angularly accelerating because there's a net torque. So R cross F for both of these two is out of the screen. Okay. So like for the force on the right, R is the vector from the axle to the point where the force is applied is to the right, and F is up. So right cross up is out of the screen. Okay, so so the torque is R, capital R, the radius of this thing, times F, and there's 2 of them. So the sum of the torques. Maybe I should write some of this stuff down. So this is example in section 10.5. There are 2 torques. Well, we're going to do sum of the torques equals I alpha. And notice I didn't write a vector sign. So I'm just going to say out of the page is positive. Or out of the screen is positive. So my vector equation just becomes just looking at the components into or out of the page, and out of the page is positive. So if the net torque is out of the page and this thing starts from rest, it's going to angularly accelerate in the direction out of the page. And what that means is that the merry-go-round is going to go from rest to rotating counterclockwise. So if you take your right hand and I told you to have your fingers in the plane of the screen and curl your fingers so that your thumb is pointing out of the screen, straight towards you, straight towards your face, you're going to have to curl your fingers counterclockwise in order to do that. Okay, so alpha out of the screen means counterclockwise angular acceleration. Okay, so we can get away with not using vector signs here. There's 2 torques. So there's R times F due to the one on the right. This rocket right here, and then there's RF that tends to rotate this in the same direction. So even though the force is in the opposite direction, the torque is in the same direction. And using the right hand rule, or sorry, using the definition of torque, thinking about this as a vector, for the rocket on the left, the lowercase r is pointing to the left, and F is pointing down. So if you have R that's pointing to the left and F that's pointing down, again, if you do left cross down, and you use the right hand rule, then R cross F is out of the page. So what I'm saying over and over again is that there are 2 torques and both of them are out of the page. So that's positive for us. So RF plus RF, that's the sum of the torques, equals I. And the merry-go-round is best approximated with a solid disk. It's not a hollow disk. It's not a sphere or anything. It's a disk. It's a cylinder. So I is going to be 1/2 the mass of the merry-go-round, r squared, times alpha. Okay. So I'm forgetting something, aren't I? Yes. So we're not just taking into account the moment of inertia of the merry-go-round, but these rockets are going to weigh some non-negligible amount, or in other words, they have some non-negligible mass. So the merry-go-round has moment of inertia 1/2 capital M r squared. The rockets, each of mass m, they have a contribution to the moment of inertia mr squared, and there's 2 of them. So all the mass is at some radius r away from the axle. So the moment of inertia of each rocket is mr squared, and there's 2 of them. So that's the total moment of inertia. So this is total for the whole system. And they're fixed onto the merry-go-round, so they rotate along with the merry-go-round, and they all have the same alpha for this system. So it looks like alpha is 2rf over 1/2 mr squared plus 2 mr squared. So maybe this one wasn't as straightforward as I thought, right? There was a lot of words going along with these 3 lines. And your book points out that, so a few things. One, first of all, we could simplify the algebra there maybe a little bit, get rid of a factor of r. And your book says that, we can, now that we have alpha, we could manufacture any number of trivial problems. So what your author means by that is that we studied in chapter 9 a whole bunch of problems with rotational kinematics. So now that we know alpha, we could ask all those rotational kinematic problems. It would apply here. But this is the dynamics of what's going on. So notice the section title is Rotational Dynamics. Okay, so we're going to do the same equation, but apply it to this problem now. So we're going to do the original problem. We're going to do this. And if M2 is bigger than M1, then M2 is going to go down and M1 is going to go up. Okay, so we're going to choose the positive direction to go along this way. So this is going to be our positive direction. Okay, so the linear acceleration of M1 is going to be A. The linear acceleration of M2 is also A. Right? The strings have different tensions, but the strings are both taut, T-A-U-T, and the system moves together with the same linear acceleration. So M1 goes, same magnitude of the linear acceleration. M1 going up and M2 going down. So let's just call that A and let that be positive. So, so for our original problem, and this is, I'm going to do this example problem in lieu of 10.6. So you could take a look at that example problem first and then look at this video, or vice versa. It's up to you. So what you've been trained to do is F equals ma, and that's still valid. So let's do that. So there are three different equations that we can create, we can set up. There's the sum of the forces on M1 is equal to M1 times its acceleration. There's the sum of the forces on M2 is equal to M2 times its acceleration. And so we can use the same A as long as we're cognizant of the different choice in positive direction for each of these. So here, this is the positive direction for M1, and for M2, this is the positive direction. So as long as we remember that for each of these two equations separately, then we can use the same value A for this. The third equation that we're going to need is going to come from sum of the torques is I alpha. Okay. So, like I said before, you've been trained in these first two ones for several weeks now. So these ones should be pretty clear. So there's T1, so focusing on M1 first, there's T1 pulling up and there's M1G down. So for this first equation, we have T1 minus M1G. This is going to be a positive quantity because this thing is going to go upwards. So the net force on M1 is upwards, and equal to M1A. For the second one, it's similar, except we just have to remember that it's M2G that's bigger than T2, which is why this thing goes down. Okay. Now, before these two, in problems that we've done like this before, the two tensions were equal and we could solve it at this point, right? We would add these two equations by elimination and the two tensions would cancel with each other. We can't do that now, though, because T1 is not equal to T2. So we need this third equation. The third equation comes from this sum of the torques on M3 is equal to I alpha. So if I look at what's going on with the pulley of mass M3, what's going on is that there are two forces acting on it. There's the tension on the left-hand side. So that tension T1 is pulling up on M1, but it's pulling down on the pulley right here. So this is T1 pulling down at this edge of the pulley. And T2 is pulling down on this end. So if you think about which way M3 is rotating, maybe you could pause the video at this point. Pause the video and try and guess, make an educated guess or reason which one of these two tensions is larger. Is it T1 or T2? So let me go back up here. Is T1 or T2 larger if M2 is bigger than M1? Okay, so this mass is going to start rotating around this way, right? And the only way so it goes from rest to rotating that way if the string doesn't slip on the pulley. And the only way it would do that is if T2 is bigger than T1. So this one is bigger. Just for emphasis, I'm going to draw it bigger, no longer line. So in other words, we kind of, just from the physical scenario, if M2 is bigger than M1, we already know how the system is going to accelerate, and we know what's a good choice for choosing the positive direction of this. So we're going to use that fact to help us out. So we already know T2 is bigger than T1. We already know the thing's going to rotate clockwise. So, so why don't we choose clockwise to be our positive direction? So clockwise is positive. Just so that when we do sum of the torques equals I alpha, I'd rather write down a positive number equals a positive number rather than a negative number equals a negative number. But in order to do that, I need to know that any torque that tends to produce a clockwise rotation is going to be a positive torque, and any torque that tends to produce a counterclockwise rotation will be a negative torque. Okay, so there's a torque from T1 and there's a torque from T2, and this is going to be I alpha. Okay. Now remember what I said, any torque which tends to produce a clockwise torque, any torque that tends to produce clockwise motion will be positive. So that torque that will be positive will be this one. T2 times the radius is actually our positive torque. So I'm actually writing it the opposite direction. So tau 2 is positive and tau 1 is negative. That torque tends to produce counterclockwise motion. So another way to see this is that if you had this vector R2 cross T2 is into the page, and into the page is our positive direction, if clockwise is our positive direction. And T1 corresponds to a torque, so R cross F there is out of the page. So these two are opposing each other, and this makes sense because they're trying to rotate the thing in opposite directions. So if one of them's positive, the other one's negative. And this is positive, right? T2 is bigger than T1. So this is a positive number on the left. What I write down on the right-hand side had better be a positive number. The moment of inertia of a solid disk is 1/2 mr squared. So that's the moment of inertia of a solid disk. And also, because we know alpha is positive, we can replace this. Otherwise, we wouldn't know whether this is plus or minus a over r. But because we just reasoned the left-hand side is positive, I know the right-hand side is positive. So this is definitely an a over r. So this is using the no-slip condition. No slip is what allows us to write alpha equals a over r. Remember in our last video, what connects the rotational, so before it was angular velocity and linear velocity, but it's also true for acceleration. Okay, so if you're wondering why that is, so if you have this, if that equation is true and you take a derivative of both sides with respect to time and r is constant, then this is also true. Okay, so this no-slip condition, you could apply it to either one of these two things. Okay, so let's divide both sides by r. And now I'm going to switch to blue. Maybe you'll see why in a second. T2 minus T1 is equal to, so look at this. There's an r squared divided by r and divided by r from this hand side. So all those r's are going to cancel. Okay, so this is just 1/2 m3a. Okay. So we have equation 1, equation 2, equation 3. And now if we add up equations 1, 2, and 3, we can solve this. It's a system of 3 equations and 3 unknowns. And the 3 unknowns are T1, T2, and A. 3 equations for 3 unknowns. We can solve for all 3. It's easiest to solve for A. And this is actually what we were asked for in the original problem. Okay? And we can see this by solving by elimination. Add up all 3 equations. And what happens from that is that T1 cancels with this minus T1, and this T2 cancels with this minus T2. So everything I just underlined cancels. And you're only left with M2G minus M1G. So you get M2G minus M1G. So I'm doing equation 1 plus equation 2 plus equation 3, and what that implies. Okay, so m2g minus m1g, all the t's have disappeared. Now when we add up all of these MAs, it's M1A, M2A, and 1/2 M3A. So A looks like it's M2 minus M1 over M1 plus M2 plus 1/2 M3, all this times G. So if you've done this problem before, you know that this answer reduces to, so if the pulley was massless, it should be the same as if M3 equals 0. So you might want to double check if you've done this problem before, on a previous problem set, for example. If when M3 was 0, the answer is M2 minus M1 over M1 plus M2. But we see how a massive pulley affects the result. So the pulley has its own mass, but because it's rotating, and that's what enters into the dynamics here, what matters more is not just the mass, but the moment of inertia. So that takes into account the mass and how it's distributed. And that's where that factor of 1/2 comes in. So actually, if M3 wasn't a solid disk, but it was a ring, you could imagine all of this stuff would look very similar, except instead of 1/2 M3, it would be just M3. Right? So just depending on the shape, that just affects the fraction in front of M3 right there. And so you can imagine what happens when you look at similar types of problems. So your book does something similar. So I think they also do a solid disk. That's probably the most common object that you would have with something like this. Yeah, and they do something similar. But I wanted to show you that you could do more complicated objects. So actually, what we did was tougher than 10.6. But you might want to take a look at that as well. Okay, conservation of angular momentum. So again, I'm going to write down the translational and rotational versions of some things. So translational version of momentum, or what led to conservation of momentum. So see how the title of this section is called Conservation of Angular Momentum? Let's try and guess what the conditions are for when angular momentum is conserved. So the translational case said that if, so let's see, so we had integral of sum of the forces over time. So I'm reminding you that so Newton's second law was sum of the forces. We'll do this. Sum of the forces is dp dt. That was the starting point here. And later on, we're going to need sum of the torques equals dl dt. Okay, when we do the rotational version, we'll look at that one. So sum of the forces equals dp dt. If you multiply both sides by dt and integrate, you get this. So this is true for any particle, and if we're to generalize to systems, then we can just look at external forces, and this we can replace with the total momentum of the system. Okay, so there are also the system versions of these equations, not just for an individual particle. And so the statement was that if the net external impulse was 0, if the net external impulse is 0, then momentum is conserved. Then linear momentum is conserved. So again, you can pause the video and try and guess what the rotational version of all these things is. So rotational. Integral of the sum of the torques, the external torques, is equal to the change in angular momentum. If the net external, and there's no good name for this. Some books call it an angular impulse. That's sort of the natural. If there's no word for it, then you just have to say angular thing. If the net external angular impulse, which is this, if the net external angular impulse is 0, then L is a constant. Then angular momentum is a constant. Okay, so your book says that your book does a simple case of the net external angular impulse being 0. And they say that the torque is 0. So yes, if the torque is 0, then angular momentum is conserved. But notice this also, remember we also talked about how if delta t goes to 0, then there is no external impulse. So it's the same thing here. If something happens that happens very quickly, then you can conserve angular momentum, even if there are external angular impulses. Yeah, so similar logic as before. Okay, so a lot of problems that a lot of these problems with angular momentum, they're the rotational versions of problems that you've seen before. So your book talks about this. Here's one example. You have a disk spinning around. So maybe I can give life to some of these examples. Example 1. You have a disk that's spinning around with some angular speed omega 1. So it's spinning around this axis. And it has a moment of inertia I1. And you drop it onto another disk that's not moving. So omega 2 is equal to 0 initially. And it has moment of inertia I2. So, and you're supposed to be dropping these on the same axis. Okay, so you drop the top one, which is rotating, onto the bottom one, which is not rotating. Okay. So what happens is that the two are going to rub against each other. There are internal frictional forces that speed up omega 2 from 0 to some positive quantity. So I'm imagining this is my positive direction. So it looks like the top disk is rotating counterclockwise as viewed from above. And that implies that the omega vector is pointing up. So this is the direction of omega 1, and we're going to call that the positive direction. So the frictional forces on the second disk will tend to speed it up. The frictional forces on the top disk tend to slow it down. And this keeps on happening until omega reaches some final angular velocity that's somewhere in between 0 and omega 1. So in other words, so omega 1 is the initial angular speed. I guess I'm running out of, I don't want to write a million subscripts. I'm kind of ran out of things to write. So this should remind you of like, so the linear version of this is like you have some m1 v1 and you have m2 at rest. So what happens is that m1 slows down and m2 speeds up until they reach a common final speed, and they stick together and they move together. And the same thing is going on here. So just like we used conservation of momentum for a perfectly inelastic collision for linear momentum, we're going to use same thing for conservation of angular momentum. So L initial equals L final. L initial was just I1 omega 1. And L final is going to be the total moment of inertia of everything times the final angular speed, which is somewhere between somewhere between 0 and omega 1. So this is I1 plus I2, and we're solving for omega f, and omega f is I1 over I1 plus I2. Okay, very similar to a linear momentum sticky collision problem. So this is also a sticky collision, but the rotational version. Right? Something similar happens if you didn't drop one rigid body onto another, but pretend you dropped a point particle. Okay, so example 2 is very similar to example 1, except you drop a point particle. So this thing is initially spinning, again, omega 1. It has I1. Except this time you drop just a mass at the end. So this you let it drop and stick onto the edge right here. Okay, so no external torques here in the up-down direction. And we're assuming it drops not too high. If it is dropped high, then maybe you're going to get the disk to start rotating this way, but we're going to assume the no motion along that direction. So another thing you could think about is just gently place this mass, just gently drop it onto it, the edge from there. So if that's the case, then it's the same result as this one, except I2 now doesn't have, there's no complicated shape, it's just a single mass. And so here, it's the same as example 1, but with I2 equal to the moment of inertia of a point mass at radius, at a distance capital R from the axis of rotation. Okay, so it's the same exact thing. You just plug this in for I2, and that's exactly what your book got. Okay, so then your book also talks about a figure skater. So this happens, so someone's spinning around and they bring their arms in, which is going on in this picture, which reduces their moment of inertia, right? They have the same mass, but it's distributed, the mass is closer to the axis of rotation if the arms are brought in. So if you reduce I, you increase omega if angular momentum is conserved. So the figure skater can speed up. So if they decrease the I by a factor 2, omega increases by a factor 2. And then your author points out that this doesn't conserve energy. And we don't expect it to conserve energy. Like, energy isn't conserved in inelastic collisions. Here, actually, the kinetic energy increases because it takes work from the figure skater's muscles to actually pull in their arms like this. So actually, it takes work, and they add kinetic energy to the system in doing so. Okay, that takes us to the end of chapter 10.